In this video, we'll look at techniques for extending our linear regression model to the case with multiple explanatory variables using multiple regression. So the multiple regression model is really simple once you're familiar with the basic linear regression model. Essentially, we just add more terms to our original linear regression model. So where we would previously have a single x, now we have x1, x2, x3, all the way up to p possible explanatory variables. Each one then gets its own slope coefficient, its own beta. So why might we want to extend our model? Well, having multiple explanatory variables in the model can be a good thing, especially when you're looking at data from large experiments or large studies where you have many variables that you want to incorporate. Multiple regression models are very flexible. You can add additional terms or you can add functions of your variables. So for example, y equals beta 0 plus beta 1 times x plus beta 2 times x squared is still a linear multiple regression model because you have a coefficient times a variable. So we can add squares, we can add cubes, we can add transformations, we can add other binary identifiers into this model. So it becomes very flexible when you start adding more variables. So we'll look at a set of data regarding pulse for a study that measured heart rate for young adults. So our variables here include active heart rate, resting heart rate, smoking status, gender, exercise habits, height measured to the nearest inch, and weight measured to the nearest pound. So what we'd like to do is try to develop a model to predict active heart rate using 3 explanatory variables. We'll use resting heart rate, height, and weight. So these 3 variables will all be incorporated into the same model for predicting active heart rate. Of these 3, let's see which one will likely have the strongest relationship with active heart rate just by plotting all 3. So when we look at height versus active heart rate, there is a slight negative correlation of negative 0.18 as height tends to increase, active heart rate tends to decrease. Weight has almost no correlation, and in fact you can see that the linear line, or the linear trend line, if we added it, is essentially flat. As weight increases, there really isn't an overall effect on a person's active heart rate. However, as you might expect, there is a strong correlation between resting heart rate versus active heart rate. So one would imagine that if we created a model with all 3 of these variables, resting heart rate should probably be the most important one. So let's write our multiple linear regression model. So our multiple linear regression model goes like this. Our predicted active heart rate, y hat, is beta 0, some basic intercept term, plus beta 1 times x1, plus beta 2 times x2, plus beta 3 times x3. To fit this multiple regression model in R, we use a plus sign to simply add more variables to our model. So our linear model now takes active heart rate as a function of, or depends on, height plus weight plus resting heart rate. So we now just have 3 explanatory variables included in our model. So our fitted multiple regression model now has 4 coefficients, 1 for the intercept and then 1 slope for each variable. So our fitted multiple regression model is 57.26 minus 0.88 times height plus about 0.11 times weight plus 1.13 times resting heart rate. So interacting with this model works just like it does in linear regression. For example, to make a prediction, we'll just plug in our x's. The only thing we now need to keep track of is which x goes where. So for our study, subject 6 has an active heart rate of 109 beats per minute resting heart rate of 65 beats per minute, was 74 inches tall, and weighed 188 pounds. If I want to predict their active heart rate, I'll simply plug these into the appropriate spots in our model. So the first variable in our model is height, so there's 74 inches. Second variable in our model is weight. Third is resting heart rate. So we predict an active heart rate of about 86 beats per minute. Our residual we calculate in the same way. It's the difference between observed and predicted. So predicted value minus observed value, we get negative 23. To interpret this model, we can test our coefficients in two ways. We can use either a hypothesis test, like we did in the previous set of notes, or we can use a confidence interval. So now looking at the summary output of our model, we now have 4 hypothesis tests, one for each of our coefficients. All of them have essentially the same set of null and alternative hypotheses. The null hypothesis is that the coefficient is equal to 0. The alternative is that it is not. The effect of resting heart rate is the strongest, as indicated by the fact that it has the smallest p-value of the bunch. So there's definitely an effect of resting heart rate. Height and weight are there. They have small p-values, but the evidence for them is not as strong. Now we can also get confidence intervals for the coefficients in our model. We can do this just by asking for confidence. So the function is confident. We insert our model, or we input our model to that function, and we get 95% confidence intervals by default for every single one of these coefficients. So for example, we might interpret the heart rate coefficient, or the resting heart rate, or sorry, this is the height coefficient. We might interpret the height coefficient like this. We're 95% confident that holding everything else constant, so weight is not changing, resting heart rate is not changing, the average change then in heart rate for every 1 inch increase in a person's height is between negative 1.68 and negative 0.08 beats per minute. These confidence intervals are all independent confidence intervals, so they are assuming that you're representing the change when all other variables are constant. So only one variable essentially is allowed to change at a time with these confidence intervals. To test the overall effectiveness of a multiple regression model, now that we have more variables, we want to know if our model is effective overall. We'll actually use a form of analysis of variance, which is kind of cool, that linkage between the two techniques. Analysis of variance in this context is testing the following hypotheses. So the null hypothesis is that the model is not a good fit for the data. The alternative is that the model is a good fit. Where this test is being executed is the very last line of the code. So this F statistic here is measuring the overall effectiveness of the model. So overall, our p-value is very, very small. There's strong evidence to reject our null hypothesis. Overall, the model is explaining or predicting some information using height, weight, and resting heart rate. In multiple regression, we have that coefficient of determination as well. So in simple linear regression, R-squares measures the proportion of variability in the response variable that can be explained using the linear model. It's the same idea in multiple linear regression, however, the interpretation, or the calculation, is not quite the same. In a simple linear regression model with just one explanatory variable, R² represents the correlation between the x variable and the y variable squared. Because we have multiple x variables, we don't want to calculate multiple coefficients of determination. So what we do is then take the correlation between the predicted value y hat and the observed value y. So that's what we're measuring with this new coefficient of determination. Now, when we're trying to choose the best model, because there are going to be multiple models that we could check, we could add variables, we could delete variables, our goal is going to be to explain as much variability as we can with the simplest possible model. Now, unfortunately, the more variables we add, the more this r squared will go up. This never decreases. So what we end up doing is adjusting this r squared, and we adjust it downward based on the number of observations in the model, n, and the number of variables in the model, here represented with a k. That's why if you look at the output, there are actually two r squares. This multiple r squares represents the squared correlation between the predicted value and the observed value. This adjusted r squared is weighted downward based on the number of variables. When you're trying to explain the variability of your model, keep with this multiple r squared. However, if you're in a situation ever where you're trying to choose between models, that's where we might recommend using adjusted r squared as a selection method instead. So how much of the variability in active heart rate are we explaining using this multiple regression model? Well, according to our multiple r squared, we're explaining about 38% of the overall variability in active heart rate. Now, there are a lot of other variables that would likely be able to explain this. Certainly age would have a factor. Amount of exercise a person gets would have an effect as well. But overall, this multiple r squared, not too bad. Now, let's say that we want to make predictions with this. So we have a new individual that is 70 inches tall, weighs 225 pounds, and has a resting heart rate of 68 beats per minute. Certainly, we could plug things directly into the model and make a prediction. So here my prediction is 97.77 roughly. But as with most other things we've learned this semester, there is an easier way. Additionally, what if we want a confidence interval for this active heart rate? What if I want to know how much I would expect this to vary? Well, we actually have a choice to make. There's two confidence intervals that we can use with a multiple regression model. We can use a traditional confidence interval, or we can use what's called a prediction interval. So the confidence interval gives an interval or a range for the mean value of y for all members of the population at a particular combination of x. So essentially what this confidence interval does is tell us where we expect the population mean response to fall. Contrast that to a prediction interval, which gives an interval for a range of values that we would expect a new observation to fall under. So if we want to know what we should expect for a single new observation, we'll use the prediction interval. The prediction interval is always going to be bigger than the confidence interval, and the reason for that has to do with the variability of the mean. When you take an average of multiple observations, you decrease that variability. We've seen that time and time again. The bigger your sample, the less variability there is in your sample results. Your prediction interval is essentially a technique where you're trying to find a confidence interval for a sample size of 1. So that's going to have a lot of variability to it. In R, we can calculate these two intervals using the following. So the first thing that I need to do is create a new data set with my input variables. So I'll call this new x. My new x gets the height variable. Height is set to 70. Weight is set to 228. Resting heart rate is set to 68. This function here, tibble, is used to create the data set. We'll then predict For our model, our new data is this new X tibble. We can calculate either a confidence interval or a prediction interval. If you notice, the difference between the lower limit and the upper limit of these confidence intervals is pretty dramatic. So based on this, here's what we can really say. We're 95% confident that the population mean active heart rate for someone with these characteristics should be between 91 and 102. So this is the population average. A new observation or a single individual with these characteristics, we would expect to see anywhere between 66 and 126. So there's a lot more variability with what we expect for a single person. Now let's say we want to investigate whether the relationship between two numerical variables changes depending on some categorical variable. So does the linear relationship change depending on gender? The simplest way to do that is this. Fit two separate linear models. We'll split the data up. We'll look at the females, fit a model for them. We'll look at the males and fit a model for them and see if there's any major differences. So in this data set, a 0 is used to indicate a male, a 1 is used to indicate a female. So we have both variables or both groups plotted side by side. For both genders, there's an increasing trend in the data. The regression lines might end up being just a little bit different. So let's find these two linear models, and for simplicity's sake, we'll use just a model with breast as the only explanatory variable included. So I'll create a new data set by filtering out all of the observations where gender is exactly equal to 0. I'll call this male. I'll use that new male data to fit a model. I'll call it model M, and I'll get my summary. So model M, for the males, we're explaining about 28% of the overall variability. The model is significant. For the females, we're explaining quite a bit more of the variability. We're explaining about 42% of the overall variation for the females. Our resting heart rate is still significant. At home, take a moment to test your knowledge. How could you find the correlation between active and resting heart rate for females? So I'll let you ponder on that. Let's take a look at one last example with multiple regression models and see what happens when some variables maybe aren't as important as we think they are. So this is the nursing home data set. We've got a data set from a sample of 52 small hospitals in the state of New Mexico. We want to predict monthly revenue. So we will use all of the numerical variables in this model. So patient revenue might change depending on the number of beds in the facility, number of inpatient days, all patient days, nurse salary, and facility expenditures. Here is the result of fitting that model. So it looks like there are two variables that are pretty strong predictors. The number of beds is a good predictor, and the number of all patient days is a good predictor. The number of inpatient days, nurse salaries, facilities expenditures aren't really contributing anything to this prediction because their p-values are quite high. The other thing to notice about this model is that our multiple R squared is very high, about 87%. So we are explaining quite a bit of the variability in patient revenue with this model. Many statisticians will tell you that if you have variables that are in your model and not explaining much, you should delete them. So here, we'll drop the variables that are not significant, that have those large p-values. So our new model only contains those two variables that we thought were important, beds and all patient days. Certainly, it's much easier to interpret and work with a model with two variables rather than 5. Take a look at what's happened to the multiple R squared. It's gone down slightly. It's gone down to about 85%. So dropping 3 variables means that we're only losing about 2% of our ability to explain patient revenue, which I think is worth it for a simpler model. So we will stop here with multiple regression, and that's it for the videos for this semester. Have a great day.